And so far we have learnt about permanent magnets and the simulation of permanent magnets. In this tutorial example, we will learn about electromagnets. Let's take an example where I have a bobbin and a coil. Let us take a closer look at the coil. So let me go ahead and hide the bobbin so that we understand the coil better. Notice that the coil has been split into two equal halves. And the reason to split the coil into two equal halves, as you will shortly see in this demonstration, is the requirement for us to compute a cross-sectional phase through which the current is designated in EMS. Now let me go back, show the bobbin, and then let us proceed with trying to simulate the magnetic field around the coil. And also the next objective is going to be to compute the inductance of this coil. To simulate the magnetic field, we would like to create an air geometry around the coil, just as we did for the magnets. So let me go ahead and create a new part where I'm going to create a rectangular air geometry covering the coil. In the last video, we discussed how big should the air geometry be. So let's make sure that we create a sufficiently large air geometry. Later we'll come back and check if it was large enough. Then we need to use the cavity option in SOLIDWORKS to subtract both the coil and the bobbin from the air geometry. Make sure that both these components are selected. Finally, let us go ahead and rename the air geometry. And we exit out of the part mode. I can choose to turn on the transparency so that we can clearly visualize the coil. Now we go on to the simulation part. To do a simulation as before, we go to the EMS manager. In this EMS manager, let us create what is called as a new study. Since we are going to study a coil that is DC excited, let us pick magnetostatic as the study type. Since we want to compute the inductance of the coil, we are going to check this option, compute circuit parameters. When you say OK, a study is created for us. The next step is to assign materials. We're going to create the material air from our favorite material to the air geometry. Next, the coil is made of copper. So let's check apply materials now to go into the material library of EMS. Here we will seek the conductor material folder and select copper and select the apply and close button. Finally, the bobbin is made of a non-magnetic material. So let's go ahead and go to apply materials. And here I select the cable, and then let's just pick any kind of a non-conducting, non-magnetic material such as nylon. Notice that the material of the bobbin, which is non-magnetic in this case, does not affect the results. So you could as well create any non-magnetic material for the bobbin, and you will get the same value for the inductance and the distribution of the magnetic field. Next, we go on to the definition of the coil. To define a coil, we right-click on the coils folder and select wound coil. We use the wound coil because the coil is actually wound by taking small wire gauge of copper and winding it around bobbin. The first thing you have to do is select the geometry of the coil. Make sure that you select both the components, both the bodies of the coil. Then we come to the entry port. This is where we will select this cross-sectional face. So I use the select other command and make sure that you select the cross-sectional face here. Because it's a complete coil, we are going to use the option same as entry port for the exit port. Finally, let us click the show preview to make sure that we have selected the right face for the coil. It looks okay. So let's go to the general properties. Here is where I would specify the wire gauge or the diameter of the wire that is used to wind the coil. In this case, I'm going to use 0.29 millimeters. And finally, also give how many conductors go through the cross-section area. So 1253 conductors. EMS automatically computes my filling factor, which is around 68.5%. That tells us that we can accommodate so many turns of 0.29 millimeter copper wire in this volume. We can leave the coil type as current driven, and then you can choose a magnitude for the current. Here I'm just going to leave it as 1 amp, so that the total amp turns that we have is 1253 amp turns. This concludes the definition of our coil. Next, let us go ahead and mesh our parts. So here we have a mesh density. We can change the slider. So let's move and make it a little bit fine. Also, in the mesh options, we can specify a growth rate for our mesh. This is really the growth rate of the size of the mesh from the smallest element to the largest element. So we can specify a tighter growth rate so that the elements grow smoothly and slowly. And then we will select the run analysis after meshing option and then select OK. EMS will mesh and solve the problem so that we are ready to take a look at the results. The solution has been completed and we are now ready to take a look at the results. The first result that I would like to plot is the magnetic flux density in a logarithmic scale to ensure that we have a right enough airbox. So let me just double click on the magnetic flux density. I go to chart options and I scroll down, select color options, and then pick the logarithmic scale. The linear scale is the one by default, so I want to pick the logarithmic scale. Notice that the values are all uniform and they're all almost made of a single color. This kind of tells you that the size of the airbox was sufficiently large. The next thing that we would like to do is to study the inductance of the coil. To calculate the inductance of the coil, I double click on the results table. In the results tables, EMS gives you several quantities which are very important. The first quantity is the resistance. So the resistance of this coil is around 25.9 ohms. Next, we go to the inductance. EMS calculates the inductance That's close to around 23 millihenry. Okay. Notice that EMS also gives you a flux linkage associated with the coil and the total amp turns that we had for this coil. Finally, we can plot the magnetic flux density as a section plot. To do that, I right click on the magnetic flux density. I go to the fringe plot and select section clipping. May want to select the inside out option so that we see the coil, and as you zoom in you can clearly see the magnetic flux density in and around the coil. To actually show the contours of the coil, I can pick the front view and I can right click on the white space, go to toggle items and select show model edges. That'll make it very clear. You will be able to see the contours of your coil and also the magnetic flux density in the middle of the bobbin, in the air region there, and also in the space around the coil. Select OK and we close the plot. Thank you for watching this video. See you in the next training video.